So hi everyone. Today we will try to discuss about what is POS tagging, that is part of speech tagging in NLP, and how is it implemented using hidden Markov models and Viterbi algorithm. So let's get started. So first of all, let's understand what is part of speech. So basically, whenever we speak something, each word has a different role in a given sentence. Some of the words may represent some action, some of the words may represent things, other words may be just joining words between two particular phrases. So, depending upon the role each word is playing, they have been assigned some tags, and these are called as part of speech tags. So, you must have heard of verbs, nouns, adjective, etc. These are all part of speech tags. Now, before we move ahead, we must know what are Markov models and hidden Markov models. Though I have explained them in my previous videos, I'll just give a brief here. So Markov models are basically a model that represents the probability of sequence of random states. Looking at this particular diagram, you can see that there are three states present in this environment: hot, cold, and warm. And eventually, what is the probability of moving from one state to another is represented by this hidden Markov chain model. So you can see that from cold to hot, the probability of transiting is 0.1. Similarly, from moving from hot to warm, it's 0.3. So similar on this ground, we have a model that tells us about the transition probabilities of moving from one state to another. Now, what are hidden Markov models? Basically, in certain cases, we have two sets of states. One is observable states, and other are unobservable states that can be derived from the observable states. For example, depending upon the rain, depending upon the weather, some person would be choosing his task. That is, either he can go for walk or shop or clean. So, in this case, first of all, our observable variables states are the weather, that is rainy and sunny, as you can see in this diagram. But eventually, depending upon these observable states, there are three hidden states present in the environment, that are walk, shop, and clean. And eventually, you can see that using the dashed lines, how one can transit from an observable state to an unobservable state. I have been moving a bit quick here because I have already explained Markov models and HMMs in my previous videos. So if you wish to go in detail, you can go there. Now coming on to the main crux of the this post, that is, why do we need hidden Markov models for POS tagging? So if you look very closely, POS tagging do resemble with hidden Markov models only. So we have a sequence of words with us. Like for example, if we have a sentence, Raju is a good boy, and eventually we wish to derive the POS tag for each word. Now eventually, if we consider either the words or the POS tags as observable states, the other automatically becomes an unobservable state. So you can make sense, right? Depending upon whatever has been given to us, we can derive either the sequence of words or either the sequence of tags for it. And eventually, hidden Markov models, that is why we would be using hidden Markov models for determining POS tags. So let's first of all know a few terminologies that we would be using in the below descriptions. One is Q, that is the total number of n states, that is the observable states we are talking about. A is a probability matrix for transition probability matrix, that is transitioning from a known state S1 to a known state S2. So, for example, in our above diagram, moving from what is the transition probability of moving from rainy to sunny or sunny to rainy can be taken as a transition probability. O is a sequence of observations that we have. B is a metrics for emission probabilities. Now, what are emission probabilities? Emission probability basically refers to transition from an observable state to an unobservable state. So, for example, when we move from rainy to walk, this probability is called as an emission state, emission probability. And the pies are initial probability distribution. So, in Markov models and hidden Markov models, one thing that I missed, like in my previous video, you can go. That is, I asked you to visit that video. The next state depends only upon the current state and not on the past states. So, for example, if we wish to determine what would be the weather tomorrow, and if it is a Markov chain, so eventually tomorrow's weather will completely depend on today's weather and not on yesterday's or day before yesterday's weather. So, when we're talking about initial probability distribution, that one state that we need to get started with when we don't have a background, when we don't have a historic information. So, that is called as an initial probability state. So in this diagram, you can see when we move from the start node, So the initial state can either be 0.6%, the probability for rain is 0.6, and the probability for sun is 0.4. So I guess we are now pretty much clear with what we are trying to do. So let's understand how this terminology we would be using in the POS tagging. Set of possible tags. So in POS tagging, what we would be doing is eventually we would be considering the POS tags as the observable states, and the words as an unobservable states. So Q becomes a set of possible tags in our case. A A, as we told about, is a transition probability matrix. Hence, we would be having transition probability matrix from moving from one POS tag to another. For example, if we wish to calculate the transition probability for a verb given a noun, that is currently the word is noun, and we wish to know what is the probability of having a verb next. So it can be given by this formula: count verb and noun coming together upon count of verbs. Sequence of observations, words in the sentence. The emission probabilities would be given by, given a tag, what is the probability of a word to have. So for example, the probability of having playing given the word is verb. You make sense, right? Emission probabilities are basically what is the probability of moving from a known state to the hidden state that we wish to know. So here the known state is verb, and the unknown state is the word that we are trying to know about. So that is why we would be calculating for, this is one of the examples that I have given. Playing, given we have a verb. So if you look at this particular diagram, these rainy and sunny get replaced by the POS tags, and these hidden states, workshop and clean, get replaced by the words in a sentence, right? And this is how HMM helps us to know the POS tag sequence for a given sentence. I think this can be a bit confusing, so we would be moving here. You can see in this example how we have got different POS tags in the state as observable states, and now different words. Here you can see P will given verb, the given verb, back given verb. So depending, so the POS tags becomes our known states, and the words in the sentence becomes our unknown states. So hence, emission probability would be moving from a what is the probability of having certain word given a given tag, and transition probability would be what is the probability of having a POS tag given we have a certain POS tag Y. So what is the probability of having a POS tag X given a POS tag Y? I think this can be a bit confusing, right? So eventually, let's jump onto the algorithm, and we will then go to an example. So to extract the POS tag sequence for a given sentence, we follow an algorithm called as Viterbi algorithm. It's pretty very popular algorithm, founded by the founder of Qualcomm. So let's first of all jump into it. Let's assume example sentence as well. Janet will back the bill. So assume that we have this sentence, and we wish to know the POS tag sequence for this sentence. Now the first step basically is to create a Viterbi matrix, or lattice that we call it. Let's try to understand how does this lattice look like. It can be like, just ignore the shades, different shades that are present, and consider and like focus on the values present. So you can see that we have column names as the words Janet will back the bill, and the rows are basically determined by the known POS tags out of which we wish to pull out tags. So there can be multiple POS tags, but here we have taken a set of tags. So a Viterbi lattice can look something like this: n cross m, where n equals to the total number of POS tags we know. Like here it is 7. DT, RB, NN, JJ. These are different POS tags, and the words of the sentence for which you are trying to get the POS tag becomes our column. Now, once we have this matrix n cross m, how to fill these values, we will come to know slowly. So we will be following a particular formula, that is v underscore t braces j equals to maximum v underscore t minus 1 into aij into b underscore j o underscore t. I think these notations can be a bit difficult to understand. It's one of my oldest blocks, so I really don't know how to format in Medium. So I will explain you what is the meaning. V t minus one, t minus one, where we are whenever we are talking about is the previous Viterbi probability. So Aij is the transition probability moving from previous state Qi to Qj, and Bj Ot represents uh, emission probability basically for the given POS tag. What would be the emission probability if we have that particular word? I think it could be a bit confusing, so we will use an example below to understand this. So first of all, let's create a transition probability matrix. So as we know earlier, we have been considering our. Don't worry about the above explanations. We will be going through an example, and everything would be very clear. Uh, we will be first creating a transition probability matrix from our corpus. Assume that we have a huge corpus, and as we told about the formulas that we followed above. So probability of, for example, probability of NNP, and so transition probability matrix would generally consider it would be a n cross n matrix where n equals the total number of POS tags we have. Right. So here you can see even in the rows we have NNP, MD, VB, and similarly in columns we have the same. And so we are trying to calculate the probability for example, uh, P probability NNP given NNP is equal to 0.3777. So if the previous state if the previous state was NNP, what is the probability that the next state is also NNP? The probability is 0.377. Similarly, we can read this transition matrix. For example, probability for NN given NNP. So if the previous state was NNP, what is the probability that we have the next tag would be NN? Here you must have observed this particular token, that is uh, uh, curly the arrowhead brackets S. So this means that the initial probability, as I told you earlier, that we don't for the first token we won't be having a previous term. So in that case, if what is the probability of an NNP given it is the first token? So it can be taken like this. Next, we would be forming an emission probability matrix. So if you remember, it is the probability of moving from a known state S to an unknown state, to an unknown hidden state. So as we told you that the hidden states would be the words in the sentence, and the known state would be the POS tags. So given an NNP, the word is Janet. The probability is equal to 0.00032. Similarly, given the word is determinant, what is the probability that it is P, the given dt is equal to 0.5. So this has to be read like that. Now, moving on to the next part of the problem, to how we use the Viterbi algorithm to determine the POS tag sequence. So this is very interesting and a bit confusing as well. So if you remember, we have determined our lattice that was n cross m, where n are the total number of POS tags that we know, and m is the total words, the sentence particularly for which we wish to get that POS tag. So I think this should be visible now. So as you remember, pi was our initial probability matrix. So if we don't have a previous token, what would be the probability for the given given POS tag as the first POS tag? So if you remember the algorithm, VTJ is equals to maximum of VT minus J Aij into BJ So let's understand what was that. So it was nothing but uh, if we wish to fill out a particular value in this Viterbi lattice, assume it to be V1 because 1 is the first word and 1 is the first PO stack that for which we are trying to know what is the probability. Similarly, you can see as we are moving up in the row, we are the parameter pass increases by 1, that is 2. For state 2 it's 2, for state 3 it is 3, for state 4 it is 4. So here states are PO tags only, and we are using V1, that is VT we were talking about is the first word. So the subscript used is representation of the index of the word, and the parameter pass represents the index of the state for which you're trying to calculate. This can be slightly confusing. So if you see, probability of NNP given start is equal to 0.28, right? Initial probability. So if you remember the algorithm, there were three terms basically. So we don't have a previous token before this, so that terms we would be ignoring. We would be coming to Aij, that is the transition probability if you remember. So if you remember the transition matrix, let's look into that. So the probability of having NNP given the start token is 0.27, that is almost equal to 0.28 if you round it off, right? 0.8 into the emission probability. So if you can go back into the matrix and see. So the emission probability, that is Janet given NNP is equals to 0.32, and eventually V11 becomes 0.00009. Similarly, if we calculate for V12, that is Janet given MD as a POS tag, so we have a value 0, because if you look at it, so the initial probability, that is MD given the start token, is 0.006, but the emission probability, Janet given MD as a token, is 0 in the emission probability matrix. MD given Janet equals to 0, and hence the term becomes a 0. Similarly, if we move on to VB, given starts with the probability 0.0031, but the emission probability, that is probability of Janet given VB, is equal to 0. That is why the whole term becomes 0. Now, if we move on to the next term, will, here things becomes a bit interesting. So, if you look here, V2 1. So, as I told you earlier, the subscript represents the index of the word, and the parameter pass represent the index of the state, right? So here we would be having we again following the formula, v maximum of vti, vt minus 1 j into aij into uh, the emission probability. So the maximum probability from the past step was 0.00009, that is 9 e raised to power minus 8. So this gets passed on to here, and it's multiplied by the transition probability of NNP given an NNP. Makes sense. So here what we are trying to predict is the probability for having a will given the state is NNP, right? Having the word will given the state NNP. So in that case, we would be considering the maximum probability from the past step, that is coming from Janet, into the transition probability of moving from the token NNP, that is the state NNP, that was a previous best state, to the current state for which you are trying to calculate the world, that is NNP. So this becomes 0.9 into the probability of transiting from NNP in NNP given an NNP into the emission probability of will given NNP. I think this can be a bit confusing. Similarly, if we look at the above thing, the V22, that is, now we are trying to calculate the probability for will given the token is MD. So in that case also, we are taking the maximum value from the past step, that is 0.00009 into the transition probability for MD given NNP into emission probability, that is emission probability will given MD. So these are three terms that we need to follow up to fill this matrix. We will be filling V23 as well. V given will pass for VB. So what you're actually trying to do is to fill out some sort of a like, as we in correlation matrix we're trying to find out correlation for every each possible pair. Here also we're trying to find out the probability for each pair that is getting formed, but the method followed is a bit different. So if you look in the third value, here what we're trying to calculate is the probability for will given the term is VB. So in that case, again we take the maximum value from the past state, that is 0. Like 9 e raised to power minus 8 into the transition probability moving from NNP to VB. Why we are considering NNP? Because the past state was NNP, as it has a maximum probability, so we consider that the past state has been taken as an NNP. So VB given an NNP into the emission probability will given VB, right? And this is how we'll be filling out the values. Now as we move on to the third one, that is back, we follow the same steps, that is in the past, for the past word, what was the most stable state? Assume that it becomes it is MD, for example. So we would be considering this value max, as you can see in the formula max, it is getting you. So maximum value from the past state into the transition probability from that state to the current state for which we are trying to calculate into the emission probability of back given VB at this end, and this is how we'll be filling out this entire matrix. So let's very quickly understand how does the Viterbi algorithm works. It was creating the Viterbi lattice only. So let's understand how does the Viterbi algorithm works now. So first of all, we'll be creating a lattice Viterbi lattice, as we talked about, where of the size n cross t, where n becomes the total POS tags and t becomes our total words that we have in the sentence. Also, we would be initializing a back pointer matrix of the same size n cross t. So I will tell you why we are doing that. uh, the first column of the Viterbi we will be then using that method that we followed earlier, as I explained you. We will be filling that Viterbi matrix, and for the first column of the back pointer we will be setting a 0. So back pointer is basically to know at the current state what was the best state previously. So as it, in the first column would represent the first word and you don't have a word before that, so we will be setting it as 0. Now what we would be doing is that using a nested loop with an outer loop with all the words and inner loop over the states. So we'll be having two loops. One loop is over words and the inner loop would be on all the possible POS tags. We will be calculating the Viterbi matrix as we discussed earlier, and we will be filling that Viterbi matrix. Eventually, we will be setting up back pointer s comma t equals to previous tag. So what does this mean? If whatever previous tag we are considering for calculating a probability for the current state, we will be assigning that index in the back pointer as the previous tag. So for example, if you remember for v22, that is for the word will, and POS tag md, we were using nnp as the previous tag in calculating vt minus 1, if you remember the max value that we are using. So what we are doing is we'll be setting up the back pointer for the index md comma will equals to nnp. Now once we are running this whole nested loop and we reach the end, so we'll consider the last column of the Viterbi matrix, the last word, and take out the maximum probability for which particular state we have the maximum probability for the last word. And using that particular state, as like for example in this diagram that we have, assume that we get the maximum value at this point, that is bill at VB. Now whatever back pointer we have stored here, we will go to that point. So if for example we have back pointer VB comma bill equals to say dt, so for the previous state we will go to uh, this particular point, back pointer the comma dt, and we'll try to trace back to the previous state here in the previous word. So eventually using the back pointer, once we have filled out the Viterbi matrix, using the back pointer thing, we are trying to recollect what was the best state given each word that we have, and eventually we'll get to our POS tag.